And I would like to thank both Alyssa and Ellen for hosting us today. It's a beautiful campus. Never been here before, so thank you for doing that as well. So, Marc, you are up first.
Well, good morning. Disclaimer, I am not an AI expert. I am certainly not a programmer. But I heard about this new thing. Oh, come on. Oh, come on. I only get 30 minutes.
That's not new. That's the same as ever. You even have to do Batman.
I just hit the slideshow button.
Usually used to be online, but work.
Are you still on the SCH guest?
I switched to a personal hotspot because I could not get it open.
Is it YouTube?
No, it's just a PowerPoint.
Oh,
okay. So, how many of you have dabbled with an AI at some point? And I'm kind of surprised because, like, physics people, we invented it, but like teachers are not getting into it. So far, I will tell you, I have not had any experience where it was trying to take over the world or trying to dominate me in any way. I have found the rate of learning to be incredibly slow, like my worst student ever. It's not learning. And in reflection, I think just playing around with ChatGPT, I think that's a good thing, that it doesn't learn too fast. My biggest surprise is it's not hooked up to the internet. It's not a Google search when you check for information. It's fed information. I think last I checked, it only had information from the internet loaded up until October 2021. So that was a couple months ago, so it might be a little bit more recent, but it's certainly not up to date. So AI is all over the news. I strongly recommend Michael Smerconish's podcast on AI. It's one of those alarming ones that brings to light some of the horror stories that journalists have discovered just from their own experience. Of course, if you prod it into asking questions, do you want to take over the world? It's going to give some answers based off the information it has, based off the algorithms it has. It can't play chess. I tried playing it at chess, and it just does a bunch of illegal moves, and I figured, I'll wait a couple weeks, see if it learned anything. It's still making a bunch of illegal moves. So some of the headlines. That one didn't come into this. It's commercializing artificial intelligence. Obviously, if there's money to be made, sure, why not? Yeah, that's the alarmists. I agree with that. I love the fact that they, for no reason at all, this headline is right outside of Google headquarters, or maybe it is related. And then the counter argument. Darn it. All right, well, I was going to get to this one. So the bottom line is it's in education. It's here. And if I feel like as physics, the physics experts in our buildings, it's up to us to really embrace this and be the driving force in our schools as to how it's going to be used. Otherwise, people who are not as well informed about how AI works are going to be the policymakers and the decision makers, and they're going to do it without your input. And it's coming anyway. So I played. And I started with, okay. I asked it for a free response question for AP Physics 1. On qualitative and quantitative translation, anybody's teaching AP Physics 1? Okay, so we know that that's a big part of the exam. And it gave me this. All right. Qualitatively describe the direction magnitude of the car's acceleration. Calculate the car's acceleration at the point where the car is located halfway through a full lap around the track. And then here it just didn't really understand what I wanted by qualitative quantitative translation. Suppose the car's speed is increased 30 meters per second. How would this affect the car's acceleration at the point where the car is located halfway through a full lap around the track? Use both qualitative and quantitative reasoning to support your answer. That's not how the College Board would word a question. And it answers instantly. Okay, direction of the car's acceleration at any given point is its motion around the track is toward the center of the circle. Okay, the magnitude of the acceleration is given by v squared over r. Yep, v is the speed, r is the radius. That means the magnitude of the acceleration is directly proportional to the square of the car's speed and inversely proportional to the radius. Okay, nope. So far so good. But this is wrong. It just doesn't get it right. Let's take a moment. It just struggles with concepts. It can't grasp some concepts. And the math is correct, but the reasoning behind the math is completely off. What is the right answer? Go back to the question?
What's the question?
Oh, great, everyone's paying attention. All right, just like my students. Okay, 20 meters per second, radius is 50. I should ask the question. It's about how I ask the question. Show of hands if you say the acceleration is 8. That's the answer. Okay. All right.
And it said the speed at the halfway point is v equals 10. Okay.
Yeah, it said that the speed wasn't 20. It said if you're halfway around the circle, now the speed's only 10.
Right.
Yeah, but
Cool.
the answer is correct according to what it says. It says speed is 10.
But it's not 10, it's 20.
Well, it forgot about it. It invented its own.
That's right. And then if you increase to 30, now this one is right. If you increase the speed to 30, what's the acceleration become? It becomes 18. So that is right. Okay, so that was a little alarming. So I wanted to see if my students were sharp, they would pick up on the mistake. That's when you know they're really ready for the AP exam. Okay, so I'm going to try this with my students. So let's say we called it. Yep. So my first try with students. Okay, I asked it to just give me a warm-up question for my class. And I'm doing this in front of the students. So I didn't know what was going to come up. And they came up with this. Same question, really, right? Almost the same question. Okay, and the students, all right, they got their pencils, notebooks, they start working on it. And I give them about 30 seconds. And then some grumbling, and they say, okay. But it actually apologizes for misunderstanding my request and gave me another question. Okay. Mass of 0.5, string length 1.2, constant speed 2 meters per second, makes an angle with the vertical 30 degrees. Okay, I call it.
Okay, gotcha, thank you.
Okay, L, R, M. Okay.
Cool. Conical pendulum, like a tetherable, right? Yeah.
Conical pendulum. Right? Conical pendulum. Okay. 10 seconds of grumbling, and 5 minutes later, the students compared answers. Everybody who knew how to solve it was in agreement. First, you have to take the sine component of the length to get the radius. And then once you have the radius, you have the speed, you can get centripetal acceleration. And then the centripetal force is mass times centripetal acceleration, 3.3. And that is a component of the tension. You get the tension is 6.7.
Why so long? You just write F tension equal whatever component of gravity, and that's it.
Where's the end?
The component of tension equal force of gravity.
Yes,
So
correct.
You don't need this.
Yes, you got it. It's wrong. You gave too much information. There's two answers. Because the tension's also a component of the weight. Or the weight's a component of the tension. So there's this answer too. And I learned this as a first, second year physics teacher, how to write problems better by not giving more variables, more known information than you have. You know, you have to match up your unknown variables and how many equations you have. And basically, if you give too much information, you're going to end up with a problem where you have two solutions. And ChatGPT did that. And doesn't realize there's a problem. Let's see if it can figure it out. So it's saying here that there's two solutions because you can identify two different frames of reference. That should not affect the outcome. So it's this is just wrong again. So make the problem well defined. We need to specify the direction we consider to be positive. I don't agree with that. I just tell my students, let towards the center always be your positive direction. Oh, I have a spelling, okay. What the solutions to the problem? Okay, so what's the answer? And for the first time, it got a little creepy. It drew a free body diagram. Badly. I don't know if that's an arrow or V for velocity. I had to go back. I thought it was a ball. It is a block, so. Yep. And the weight is now just G, not mg. I'm looking for the angle, and I figure, well, you know, if this thing's going around in a circle, if you just like stop where it is between you and the center of the circle, this is not it. You know, maybe the string here is going inward, so give it the benefit of the doubt for the perspective for that 30-degree angle that you don't see there. But this creeped me a little bit because why would a computer need a model to answer a question? And I wasn't sure which was going on here. I'm still not. What do you think? BJ.
Even looking like above the doorway there, it says, I will always draw a free body diagram before I pose a problem, right?
Good advice.
Physicists are trained to do it, and every problem that says, this is the solution, which you're going to be drawing from, says, draw a free body diagram.
Okay, so based on the information it has to answer my question, it's going to attempt free body diagram. I'm hoping that's it.
My thought also is that, okay, so this thing is trained on a huge data set.
Yeah.
And that huge data set is all text and characters. This thing doesn't really understand images all that well.
Correct.
But some part in that data set, somebody used ASCII characters to make free body diagrams.
Yeah, I think it's like similar to what Marc said. So somewhere in its background of information, it had free body diagrams in its memory. Ron.
I think another problem might be that it's a large language model, LLM. It is really, really good at language, and it's not particularly good at this sort of thing. And when we try to use it to do things like investing, giving us investing strategies or solving physics problems, it can give, it hallucinates, it starts making up answers where it doesn't really know the answer.
Right.
And it communicates in really convincing language.
Yes,
And
absolutely.
I think that's a big part of the problem.
Yeah, it does. It does explain
To
it.
that idea that somewhere it saw an ASCII free body diagram.
Yeah.
That's the sort of thing it's good at.
Yeah, and I don't envy the English teachers because if this does make convincing arguments, and once the concept is wrong, like if the student tries to use ChatGPT, I'm not worried now because I know like it's it's not, and that's a whole other ethical issue.
I'm
Paula.
just wondering, the question that it got wrong in terms of halfway, I wonder if you had, the question and you gave the answer, the correct answer, would it have been able to?
Let's try it.
Yeah, I'm just.
Oh, my session expired. Let's try it later, but we could try it.
Yeah, I wonder if it was able to modify its answer so that it could logically come up with.
Yeah, and that's, I mean, I encourage anybody to try that. Like and this is just, one question I asked it. I was playing with it, and asked a bunch of different questions, and it seems to always come back to, does it understand concepts? Is it able to handle just
And I wonder
basic
if
concepts that we expect our students to know?
I wonder if it gives the same answer next time you ask it. You know what I mean?
Right. That I did see some consistent arguments, I would say. And your questions that lead to the same answer. I hope so.
I don't think this is the case, but I know with the AP1, they often give students are observing some scenario, and 3 students give their 3 explanations.
Oh, yeah. The
So
conflicting
maybe
contentions tests.
Using this as a teaching exercise for you, tell me what I did wrong.
Right. Yeah, so it is.
I don't think it is, but.
It is good for conflicting contentions tests. I'm trying to write one of those questions. I can get the wrong argument.
Multiple times.
Right. Bruce.
What did your students think of all this? Because I'm thinking that I could recognize myself in the early times when I wasn't sure.
Well,
I could throw a bunch of baloney on the page and hope that the teacher didn't actually read my homework.
well, your students are already playing with this. They're already trying it.
Well, I meant it's regarding physics.
The takeaway I wanted them to get is it doesn't understand concepts. You're going to get it wrong, so don't try it. Which is not the most positive message, but I think I was effective in conveying, it's don't try. They shouldn't be. I want them to play with it. It is the technology of the future, but I certainly don't want them to use that for their work. And I think the obvious takeaway was, it's going to be wrong. It's one of the worst students I've had ever.
Well, at least it apologizes.
Wrong for the next 6 months.
That's right.
And this is evolving really fast.
This is true. This is true.
Really fast.
So we had ChatGPT write a question on our last test, and I would trust it to write questions, but not to solve them, and not to put a question. I'm not going to put anything blind that this thing poops out. But we did actually use it for that. We wanted a conceptual question about what, like work or something? Force?
Yeah, it was about, it was the one about, it was a friction problem.
Yeah.
We wanted a conceptual problem about coefficient of friction for 9th grade.
Yeah, and it did do a decent job, but we had to check it with our minds. What I have been using this for regularly over the past 2 to 3 months is it writes most of my parent emails.
There you go. Parents will never figure it.
If you tell it, I'm a teacher and I'm writing an email to, I want the tone to be, and here are the key details, it actually writes really good parent emails. Not that you're going to send without looking at. But it writes most of my communication home to the team I coach, and the kids know. I'll tell them.
Did you ask it to write a rubric for that question?
No, I don't trust its rubrics. I've asked it to write rubrics because I've played with it a lot, and it's good at throwing rubric-y jargon down. But
Yeah, we didn't ask it for an answer for that
no, we didn't.
question.
I actually asked it to write. I asked it for a prompt, and then it gave me 10 different options. It gave me a scenario and 10 different what is the this? How could you do that? And we just selected a few. So it was just for idea generation. But parent emails, it's a winner.
Wow.
Okay, so this goes into the explanation a little more, and it has some things wrong here. It can't do components. It's just like my students in that respect. Just can't do component. The 30 degrees is not even here anymore. Just gone. Tension equals centripetal force now. We got the radius right. Got the radius right. But then tension equals centripetal force again, so that's not right. So I asked it what happened to the 30-degree angle, and it's still trying to BS its way through a response, making a convincing argument.
So
and it's sticking to just the component of the radius, but not the component of the tension. And I got just a couple minutes, so I'm gonna. Okay, so it continued with responses that were just convoluted and just not correct, but very convincing sounding arguments. So again, I don't envy the humanities teachers. They're going to have a tougher time sifting through. And as far as I can tell, the software that will tell you what percent of an essay was plagiarized, if it's generated by an AI, it's original. So there's another ethical question: who gets the credit? Right, so again, the fact that this is learning, so I have the free version, so of course it's gonna learn a little slower maybe. I think that's still a good thing. I still think everybody should try it and be a leader in your school with this. Was there another hand? Yeah,
Yeah,
Bruce.
I can't believe you didn't come back and say, why are you asking me all these questions? I did the problem, leave me alone.
Yeah, it might get to, yeah, well, that's I think deep down that's our fear, is eventually AI is going to get tired of us humans, right?
And take over the world.
Yeah, right.
Unlike students, it's smart enough to know you don't piss the teacher off.
Mark, I think I'm in Princeton. I think someone at Princeton has it up ChatGPT 0 or whatever. It can figure out if something's been ChatGPT 98% accurate.
Ah,
It's
okay.
called GPT 0 or something. I forget.
Okay.
That sounds right.
So-
Something like that, yeah.
Okay, I did not go past the free version.
There's a big headline about that teacher accused a student cheating using ChatGPT 0, and they were incorrect, and it's like national news.
Oh,
So
lovely.
There's warnings out there, like even the people who design ChatGPT 0 tell you it isn't always right.
Yeah, that's one of the problems at Quinn University we're talking about. We're having a discussion on this, and the issue is those can only give you a probability or some metric, but that is not proof of.
It's not a proof. Having a percent that's the same is.
Even if it's a high percent, it does not matter. It's not proof of cheating.
Well, I know one English teacher in my
There you go. Regardless, they didn't use ChatGPT.
One English teacher in my school, every essay now, the kids come in, there's a piece of paper and a pencil at their desk. And there's, how else are they going to, make sure it's original now? Okay, so the takeaway, what's coming down the pike? Your school is going to have policy on this. I encourage everybody in this room to get involved with that process so that you can help those who are not as informed as we physicists to make the right decisions for our students. Most of those policies will probably be along the lines of plagiarism, how we define plagiarism, which should include artificially generated material, and your kids are already using it. Okay, maybe the parents are already using it. So we should be checking it out as well. Bruce?
One of the things that came up at that time is students hiring somebody to do original work for them and turning it in as their own.
It's old-fashioned.
I don't know how to think about that. Is that plagiarism or is that just delegating?
Just academic dishonesty. Just
That definitely would be, doesn't pass the smell test in my district, that's for sure.
At least with ChatGPT, it doesn't give you references properly, or it doesn't give you real references. So at least there's that. For now.
Right.
Yeah, I mean, really, it's almost useless to talk about this because it's different by the time we walk out the door.
Yeah.
Yeah, it does move fast. The speed of information does go fast. But thank you for helping drive this discussion. It was it's just something to think about because this is obviously very controversial.
Thank you. All right, Stu, you're up next.
I
apologize in advance because the rest of you guys have dissipated your creative juices on a daily basis, but I've been sitting around for 4 years with no class. And so...
You've had no class longer than that.
Right, thank you. So I am ready to have people to talk to. Okay, I retired 4 years ago from Penn. I ran the demo lab. I am Bill Berner. Penn is a research institution. It is a shark that has to eat constantly to stay alive. And so they constantly rotate their research labs, okay? They don't like to store stuff because storerooms don't get grants. So they throw stuff out. I lived in a 13-room, 3-story Victorian with my wife and no pets and no kids. So I didn't let them throw anything out. In the 4 years that I've been retired, I have been wading through all this crap that I had. And so I will show you layers of it as time goes on, okay? And this is among the first of the layers. So one of the things that we found, or that I found, was, in fact, I have 3 of these boxes. They told me to clean out a storeroom because they were going to turn it into a classroom. And there were 3 of these furniture-grade boxes with these stunning tuning forks. I actually brought the box in. It's back there. Have a look at it a little bit later. It defies description, the amount of effort that went into that, okay? It's fine furniture that it's stored in. It's machined steel. It's hand engraved by the guy who made it. They are adjustable. It's beautiful brass and steel. And, you know, I kind of felt like Allen Iverson, like, you know, tuning forks? We're talking about tuning forks. Like, and which is why Penn was throwing them away. And so, you know, I thought, all right, we got to look into this. I mean, there's a reason somebody put this much time in. And it turns out that, indeed, I am not only the arrogant, but also the ignorant 20th century physicist who doesn't think about doing physics without electronics. And so, in the 19th century, not only didn't they have electronics, they didn't have light bulbs, right? Like, we forget all this stuff. This was the way you time things. These are adjustable. There's a little spike right here, and they were calibratable. They had a drum that they would cover with carbon black, rotate the drum, and they could deliver a spark reliably every second. And so they could see the number, they would count the number of vibrations they had in the carbon black in a second and really nail down this, you know, the accuracy of this. If you went to school in the 20th century in the United States, they told you about the Civil War and then World War I, and there's this huge void. And, you know, what was going on in the second half of the 19th century? Well, everybody was sitting there waiting for cars and cell phones, right? I mean, you know, it was just, I mean, they were just pissed that they got born, you know, 50 years too early. There was a lot going on. In fact, as I, and you know what, God, there's a handout back there. See it next to my mug. Hurl that out at people. I'm going to propose an 1879 club. Please note, okay? In 1879, this is amazing shit. 1642 is the other year where you can see the baton being passed. Okay? Do you know that? Right? 16. Come on, guys. This is your job. Okay? Galileo died and Newton was born in 1642. Okay? Now, it's a reach because Galileo died in January and Newton was born in December, so they had to have long arms to pass the baton. Okay, but in 1879, Maxwell died, Einstein was born, and Michelson measured the speed of light. I mean, that was a big year. Okay, the entire panoply of modern physics was, birthed in 1879. Michelson, how do you measure the speed of light in 1879? I mean, there are no oscilloscopes. Michelson measured the speed of light at the Naval Academy, and if you go to the Naval Academy, you got to walk all the way across the campus. It's over near where the water is, right? If you get in on the Annapolis side. This is Albert Michelson Hall over here. And on this patio, they have dotted stainless steel doodads showing you the path that Michelson sent his light down. And there's a plaque here saying that he did such a thing. And what did he do? Well, he had an air turbine spinning a mirror. He could control the jet of air and get to where he knew how fast that mirror was turning. And how did he know how fast the mirror was turning? He took a tuning fork, put a mirror on it. It was a 128 hertz tuning fork. He whacked the tuning fork, spun this thing until the light bouncing off the mirror was synchronized with the tuning fork. He then knew that this was spinning at 128 revolutions per second. Now he's got his time. 5 significant figures for the speed of light with that apparatus. Okay, I mean, just astounding stuff. Now, where do you get your stuff, right? This is not Harbor Freight tuning forks. Okay, you need to get good tuning forks. Now, the good tuning forks were made by a guy named Rudolf Koenig, a Parisian instrument maker. Okay, working in the later part of the 1800s. And, okay, here's his catalog. The internet is ridiculous. I mean, you figure, this is stupid, but I'll try. I'll put his name in. And somebody has reproduced the catalog. So this is an 1889 catalog where Mr. Koenig is bragging about the fact that he's been to these displays in London, Paris, and Philadelphia, 1876. And so if you dig through the mushroom soil, you realize that Penn was moving from 9th Street, the original Ben Franklin site, to their suburban campus at 34th and Chestnut, okay, or Walnut, okay, in 1872. Their first physics chairman happened around that time. Now, how do you get a first physics chairman? Wasn't that Ben Franklin? Well, no. Your first physics chairman happens by accident when you hire your second physics teacher. Because now somebody has to be in charge, okay? And they go out, and obviously they're interested in equipping the department. And so it's easy to imagine that this stuff was actually purchased at the Centennial Exposition. And there's other stuff, but you only gave me 20 minutes, okay? I could take the rest of your life. All right? But we'll spread this out over a couple of years. And so we get these tuning forks. In 1857, Lissajous invented Lissajous figures. Okay, so what do? You go to Radio Shack and get one of those ICO oscilloscopes? No? How do you do that? Okay, Mr. Koenig would make tuning forks of that ilk, right? But he also made tuning forks with mirrors on them. And I've got 2 of them here. There were 3 boxes of these babies. I could only haul one of them. And so I've set this up for the Lissajous experiment. Okay? We've got one tuning fork here that is a preset tuning fork. Notice it doesn't have brass slides on it. Okay? It says RK. These are hand engraved by the maker. I mean, it's just you know, AI my ass, okay? These guys were actually doing this stuff, you know? Like, it's just astounding. This is a tunable tuning fork, okay? You can slide it around. It's marked, okay? All of these are marked pretty accurately. And what you do, right, you need X, Y, so you mount one of these so it vibrates in the vertical plane, one in the horizontal plane. These discs, one of them is silver, and one is just a balancing weight, okay? Mr. Lissajou, I doubt, had a green laser pointer, okay? It's a big help to have a green laser pointer. Yeah, we're going to do a biology experiment here and burn a hole in your head, okay?
You want the lights off?
Lights off?
Yeah, and you know what? Let's flip lights off.
You can see fine.
They don't completely go off.
Yeah, but just, yeah, that's good stuff. And let me see.
There it is.
There you go. Okay? And so we've now got our trace. And we take our soft mallet, okay, and we give this guy a whack. And now we've got horizontal motion. And we give this guy a whack. And there we've got our, and see, and I've tuned this too well, really. It doesn't drift enough. Let's hit it again and change the phase. There we go. Okay? And the other cool thing, I mean, this is really sensitive stuff. These guys are...
See the phase evolving?
yeah, because I'm not perfect, right? But I got close. But if we add the weight of a couple of pieces of masking tape, okay? And so now we do the same thing we just did. And now we get it to drift faster. And of course the rate of drift is the frequency change. Okay? So this was all done in 1857 with these things. The
Yeah, what kind of light were they using?
they were pretty good with lantern. You know, they could. I think they were probably using maybe an arc light, but probably not. I mean, that far back, they didn't have much electricity. But gas lights with parabolic reflectors.
Yeah, for sure.
Right, but you have to start pretty bright. So this is a 320 VS tuning fork. Is that a French unit? No, it's vibrations per second. Because one of Mr. Koenig's customers was a guy named Heinrich Hertz, who had yet to use this thing well enough to get his name established as the unit of frequency. Okay, so it's, you know, it's a really, really interesting thing. So we've got, you know, so Koenig was basically the Hewlett-Packard of his era. Okay, you went there to get your precision measuring tools.
So put the lights back on.
Yeah. Okay, and here's the 320 VS, and there's the RK logo. Okay, Case Western has the actual tuning fork that was used by Michelson for his speed of light. They've got it in their archive, and it's a Koenig tuning fork. And then that's just the apparatus there. If you get around to playing with this stuff, there are a bunch of things available for, you know, an iPhone. This SPL and FFT is a really nice app. It gives you decibel readings, but it also does a great job with frequencies. It's on your iPhone, you know, it's terrifying that, you know, you've got this gadget in your pocket that will do more science than the world did up to 1900. But that's, you know, if you want to play with getting your timing right. You can do this with normal tuning forks, okay? Because before I was a spoiled brat at an Ivy League school, I was a poverty-stricken Catholic school teacher. So I always think of, well, how do real people do this stuff? Auto supply store. Cut and fix your rear view mirror, okay? Sheets of reflective plastic, double-sided tape, usual tuning forks. You can set them up. Okay, the problem is these aluminum babies don't have the amplitude that the steel ones do. So you need a bright laser and a long throw. But it can be done. Okay. All right.
So can you imagine the machining technology?
I can't, because it's steel. I mean, that's the point.
And they're using water power or steam probably.
God only knows. You know,
Maybe a horse.
I mean, they had in the Smithsonian History Museum, there was a machine shop, a 19th century machine shop reproduced, and I remember it just. To me, it was the loudest statement of how important electricity was. Because it had most of the tools you'd recognize in a machine shop, except they were rigidly mounted on tables, and there were drive shafts across the ceiling with great big drums on them. So there's a water wheel outside that's driving these shafts, and you have to run a belt, or you don't get an extension cord to run your tool. You declutch the shaft and lace a leather belt on and run your tool. And you know, just, and that's kind of what was going on. But this is, I mean, the edges on this steel are sharp enough to cut yourself. You know, they're just, it's really amazing stuff. And, you know, like in my handout, I said, when I saw this, I thought, well, like, okay, so it's the late 1800s, and Kelvin has just said, well, it's over, dudes. You know, we know it all. And so, you know, what do? Well, you go out and spend your money on eye candy. Okay, so let's make really neat machinery and put it in cool boxes. But obviously, that's not what was going on. The other interesting point that I found is that Kelvin never said that. It's a paraphrase of a statement made by none other than Albert Michelson, who said that, you know, what's left is getting more decimal places. Not realizing that he had just pushed the door open to an awful lot more. Do I have anything more here? Okay. How much time do I have? All right. Wandering through the discount room in Boscov's. Yes, big change from Michelson measuring up. I found this. Ta-da! Okay, so this is the sanitizer for your cell phone if you're still afraid of COVID. Almost nobody is. They can't get rid of these suckers. The prices have come way down. Boscov's was dumping these babies for $9.95. Okay, this has a cell phone, a wireless charger in the deck, okay? But it's also got the new ultraviolet solid state light. Okay, so you say, well, I have a blue laser, you know, and it's, you know, almost, it's kind of ultraviolet-y, things glow. No, you don't. It's a piece of shit, 400 nanometer. It's violet. It's not ultraviolet, okay? This is the real deal. This is UVC. In fact, it's scary, okay? Fall asleep with your hand here and you will have melanoma, okay? 275 nanometers. This stuff wants to do photoelectric stuff really bad, okay? So at Penn, when I got to Penn, one of the best demos they had, I mean, one of the demos I wished that I had had when I had high school kids, was Penn's photoelectric demo. They had a great big electroscope that you could charge with normal static stuff. And they had a piece of machined pure zinc that would go on top of the electroscope. Because zinc as you know, is over there with, only 1 or 2 orbital electrons. It's not hanging on real tight. I mean, sure, you could use sodium if you got in there fast before it blew up, okay? But you come over a column or 2 and you get nearly stable and pretty affordable. So zinc works pretty well on the photoelectric effect, and you could use one of those party ultraviolet lights. And you could charge the electroscope and bring in the ultraviolet light and have it go. And of course, one of the things that you really should point out if you're doing this demo is that in normal room light it doesn't discharge. Okay, that it really makes a difference what wavelength you play with. Okay, so this worked really good in my basement last week when it wasn't 120% humidity. And so this light is strong enough that you don't need flashy zinc. So this is an Arbor Scientific. Penn didn't throw out any electroscopes. Can you imagine? What am I going to do? Do I have to buy something? Okay, so I got an Arbor Scientific. It's an aluminum disc. That works just fine. The zinc also, you want to get the oxide off. Okay, because the oxide really hangs on to electrons that you want to be moving around. So you polish it up with a little steel wool. I am using PVC, and this is acrylic, in essence plexiglass. These guys are pretty far apart on the triboelectric table. We take this all for granted, ask our students to believe it. It may as well be tablets from the mount, okay? We really ought to describe how does this work, okay? Microfiber is right about in the middle of the triboelectric series. So it turns out that you can charge PVC negative and plexiglass positive with the same rag, okay? Which I think, and you can do that if it isn't this shitty humidity, okay? But it is. So we'll give this a shot. I don't think it's going to go. But remember, I'm good at my job, so we can figure out how to do this, all right? It's not even crackling.
Hey, you got some charge.
I don't know. And it really is static, so you really do have to wipe it. It doesn't move, okay? You've got to wipe it on there. All right, so now we bring this baby, and we turn this thing on. And we turn this thing on.
Should we turn off the ambient light?
Shouldn't matter. What did I charge that with? Are you kidding me?
Can I say something?
Yes.
I used your demo on Thursday. And we discovered with Mary that the surface has to be really shiny.
Yes.
Super shiny.
Right, and that is the case. Right, Mary actually called me. I sent her this demo.
I was with her, yes.
But now, this should, I was surprised this worked because I'm wondering what charge I got on here. This should be negative. Settle down, boy.
I actually have it in my slide decks.
Yeah.
I heard a teacher once say, why do these demos never work the way they usually do?
Yes, absolutely. You got it. All right, the other option is to charge this by induction. So this is positive. And he's charging pretty well. And we will prove that it's positive by bringing this in and showing that nothing happens because we've already taken electrons away, okay? So it's not doing anything. So we take it away, ground this baby, and now we make this negative by induction. Okay? And then, okay? And so, you can do such things. And it is, one of the challenges of doing physics demos is, can he do this in humidity? Yeah. Okay, like, are you really good at this, or are you just faking it? Okay, 4 minutes, right. Real quick, I've got it set up back here. These little neon lights, okay? This is, the neon pilot lights. You can get them, this is 100 for $10, $15. You use them in series with a 20 or 30,000 ohm resistor. You hook them up to a variac. So you've got this variac wired in to the series of the neon light and the resistor. It's interesting to put a voltmeter just across the light bulb. And turn this guy on. And with this guy comes on. And see, it's hard to do quantitative work with AC because it's going through such a range of voltages. But we can get this guy up somewhere between 70 and 90 volts usually, and this is actually a little lower. So the light comes on. Can we flip the room lights out real fast? So we've got this guy coming on at like 51. We can turn it down a smidge, and you get one of your fake ultraviolet. So this is a blue laser, okay, and it will make this light. In other words, you're so close to ionizing it that the photon energy here will kick it. And one of the interesting things is you can take a green laser and you can actually squeak this, so it doesn't work here, it's not as energetic as the blue, but there, okay? And you can get the green to trigger it when you're really, really close. The red will never trigger it. There's a great article that I've referenced in the handout in AJP where they did this quantitatively with a calibrated DC source, and you can get to Planck's constant pretty directly. Okay? But once again, what I'm driving at here is it would be nice to get this to be conceptual. I mean, what we talk about in terms of quantum mechanics is so abstract. And it's really neat to be able to just show, the mobile charge is negative, I can get rid of them with these photons, I can't do that if it's positive. Okay, I can bring up my energy level. I think the photoelectric effect is one of the great places because, I've said failure to appreciate acceleration is the biggest way to botch first semester physics. Failure to appreciate electric potential energy is the best way to botch second semester physics. And voltage is, I think, better taught with photoelectric effect than almost anything because there's no current involved. You're really just talking energies, and it's a great place to get that point across. Done.
I'm out of the classroom now, but I tutor.
My students.
Yeah,
we share some.
and there's something that this was not part of my presentation, but it just so happened that Mark, you reminded me of something. It was sometime last month, and there was a student, and we were looking over a problem. And the problem was something to the order, there's a certain mass that's being spun in a circle. And I remember the numbers, because I actually decided to just get something and do this with the student who I was tutoring. And the numbers I remember were the length of a string was 0.7 meters. And the mass of the thing was about, I think it was 100 grams. So not very massive. And let's see, that was it. And in the problem, it said, this was, the teacher had given this problem, in the problem it said, ignore any dipping, i.e., it's in a not just the plane of the stopper was going in a horizontal circle, but that the string itself was horizontal. And solve for the tension in the string at 0.7 meters. Oh yeah, one other thing I forgot. The period was 1 second. And I said, okay, this is a little funky. And I took something, I don't know, it was a fork or something, got a string. The student was over at my house. And I spun it around in about 1 second period, about 0.7 meters long. And the son of a bitch is really drooping. There's nowhere close to horizontal. I said, there's a problem with this problem. Then I went through it, and there's an interesting, you have, let's see, equals what, 4 pi squared m r over t squared. And if you do that and say, well, remember, his string doesn't droop. L and R, unlike this, he was calling L and R the same. It so happens, if you do the derivation, you get Ft is equal to 4 pi squared ml over t squared. If you use L for R, you get Fc, or you get Ft for Fc. And there's no problem with the answer. The answer, and we had to go through this because he said, let me check after I went through it, I said, and there's a problem. He said, let me check what the teacher's answer was. And the teacher's answer just looked at, just said Fc was equal to Ft. The problem is, if you do this and use L for R and Ft for Fc, you get the same answer. And that's a problem because it's not the right way. There's something it's similar. I think it's for finding the mass of it's the radius of a black hole. And there is some derivation that you can use, I guess with general relativity, which would show the particular radius in terms of the mass of the black hole. And in fact, if you do an escape problem, and you let 1/2 mv squared, as though you're doing a regular gravity problem, 1/2 mv squared equal gmm over r, and you don't use relativity, you get the right answer for what the escape velocity would be. Excuse me, the radius. And what you do is you make v equal to c. it's not right, but it works. And that's a problem with this particular problem. When I saw Marc bringing this up, sometimes, unfortunately, and I'm certainly not one to talk, but unfortunately, we don't always have to look out for artificial intelligence. We got to look at, I don't want to say human intelligence, but it's one of the advantages, commercial, of having a group like this. So teachers who are in somewhat isolation, who maybe go on the internet to see some demonstrations or what, this is where somebody can bring out in their demonstration, like Marc did, the fact that this is not, or this is not the same as this, and I sort of wish that we would get this, again, the advertise or the commercial, we'd get more people to come to meetings like this, so you can get that interaction and see things that you just may not be able to see, even on the internet. But by the way, the following problem for the student had a car. This is a car, its headlights. And this is the plane of an inclined bank track. And you know the problem, what speed does the car have to go at to just be able, without friction, of course, just be able to stay in a horizontal level with whatever the radius is. The student's solution, guess where the center of the circle was? Right down here. And they were calling that R. And unfortunately, it can happen again when you're in isolation and you come up with a method and you see, well, I get an answer. I don't get the right answer, but I'm not going to do any experiments to test anyway. So this is why, I think that we're here. So we can mix with one another and learn things. So that's my little commercial. When I was cleaning, I have a question. I was cleaning up my house to bring something here besides just this. And I found a Super Bowl. I had lots of Super Bowls when I was teaching. And this one is at least 10 years old. And I don't know, but I picked up the Super Bowl, took it, I was going to do it here today. Nothing near super. Felt the ball, and it's like feeling this table here. There was, even though a Super Bowl is not easy to feel the sponginess of it, but I was surprised at how not only unspongy, but how how inelastic the collision was. I know, Bill, you work with cars and rubber and friction. I don't know if you know, what is it about, or anybody here, what is it about the polymer that they use in the Super Bowl that after 10 years, it's no longer elastic? Does anybody know? I was curious. Yeah, Bruce?
I would guess that a lot of the polymers become cross-linked.
Possible.
You
But
pay extra for those, they're called sad, happy and sad. Well, I think
right, I know.
I think
yes.
it's became sad.
But
Yeah.
they've started to recognize that in all areas. I mean, these days manufacturers are telling you that your car tires have a shelf life, not a wear life.
Yeah.
And that if your tires are more than 6 or 7 years old, you can't count on the rubber doing what they told you it would do when you bought the tires.
Yeah, so I didn't find a definitive answer somewhere out there, but I'm sure there is. I don't think I had a particularly weird Super Bowl because I took a couple. I have lots of things like that.
Rubber bands work the same way, you have to put them in Ziploc bags, I think.
Yeah,
So
I
that-
mean, they lose their elasticity. I don't know. Anyway, what I did find when I was looking for something, I may have shown this years ago, is, and you can get this right from Amazon, woodpecker toy. Watch your spelling. Woodpecker toy. And this little fellow goes down, starts stopping its way down. And this is a nice thing to use if you wanted to talk about friction and the difference between sliding and static friction, and also the effect of the normal force, because when this thing goes back and forth, when it's like this, there's a fair bit of torque being provided by gravity on the bird, and it pushes it into the bar. And then it's not as easy to slide. If I hold it like this and just, you can almost, I don't know if you can hear it.
Yeah.
But if you hold it like this, so I'm holding it in what would be a middle position, it's very easy to slide, and again, much harder when it's off at an angle. So this is going between static friction and sliding friction, which is fairly low, enough so, and in fact hardly any friction at all when it's right here, so that the holes is noticeably wider than the diameter of the shaft. And so each time it's right around the middle, it loses the static friction effect, and it slides, and then when it gets either here or here, then at least it slows down, and then speeds back up based on how rapidly this is going. So again, it's woodpecker toys. I think it was $8 with shipping from Amazon. Now, I don't know where. Well, excuse me, with shipping if you have Prime. So, whoops. All right, so here's what I did plan to show. And Bill had a demonstration, two demonstrations, one in the 19th century and one from the 21st century. Well, this is, I'm just going to turn off lights to some of this. This is something right smack almost in the middle of the 20th century. Film loops, which you don't see them, my guess is, too much anymore, if at all. And in the making of PSSC program in the mid-60s and Project Physics, there was a set of films that were, I don't know how many of you have seen a film loop projector? It has films that are in cartridges about yay big, and you put in, and you turn it on, and the film, it's in a loop. So once you're finished with it, it just restarts. And so this is, in a sense, the beginning. That says 1964, and the other ones are around that time too. And these are nice. I used to use them a lot. Excuse me. I used to use them a lot because they did a very nice job of showing, in reality, a particular setup, which was water in a tank. Just out of curiosity, I didn't see any, but I don't know. Do you have here?
Yeah, we have wave tanks.
You wave tank.
Stopped using them after, I had like a laptop incident a couple of years ago and gave up on them, where a kid dumped a wave tank on his laptop.
Oh, that was a shame. If you use a ripple tank and get an opportunity, the last school I taught at when I was teaching part-time, they didn't have any ripple tanks there. So, and I don't know at the time whether I showed this. I was just going through the internet a few weeks ago and typed in the word Ewing, E-A-L-I-N-G, film loops. Ewing was the company. Oh, there it is. And if you just type in Ewing and then film loops into Google, you'll get actually a series of possible ones that work. And the ripple tanks are nice because, again, they're a real thing. It's not just a simulation. We get, I mean, it's a movie of something real, but it's very nice. And so, now of course I don't pay for, I could go to full screen, but I'll just leave it here. It starts off, if you start at the beginning of the loop, it starts off with the title. And one nice thing, I just want to be sure, is well, actually, here's something. Oh, there it is. Let me go back for a second. If you start, it's nice, I guess whoever filmed these was filming the ripple tank film loop, and you hear the roar. That's the film loop projector. A very common, if you ever use them, a very common sounds. One of the things you couldn't do with a film loop is what I'm doing right there. Anybody remember why? You froze it? Right, because the film stops and that hot lamp burns it right through. And I mean, it's nothing like when, because you have one of each of these types of film loops. If you blow one out by burning a hole in it, it's pretty unfortunate. So, but these you can stop. Excuse me. And just what they're doing, in this case, for example, looking for the focal point of the parabolic arc, and when they find it, you get nice straight wavefront whose lines of direction are all parallel along the full wavefront. It's the analogy of a point source put at the focal point and getting parallel rays coming out of this is pretty cool. And it already says, which is sort of a shame, it says no spherical aberration. So you can see their first, they do drop, and it so happens that the approximate focal point for a circular one is half the radius. So they're going to be, I always used to call her she, and I don't know why. I said the dropper. So she's finding the approximate focal point, and then you can see around the edges the spherical aberration. Another thing you couldn't do, I'm just going to show the whole thing. It goes back to that, and then sending a plane wavefront, like parallel rays of light, and watching it swoop right in to the focal point. So it starts with a single one. Now you can freeze it, and you can show that at the intersection where the wavefront is meeting the mirror at that particular time, you can show that the approximate angle of reflection, which would be right around, oops, started it up, that the angle of incidence is visually not far from the angle of reflection. One thing, if you want to use a model of light, you say, what doesn't light do when it reflects off of a surface? And it doesn't, a regular mirrored surface.
It doesn't change color, it doesn't change wavelength. And you can see that in fact when periodic waves reflect off, their wavelength as they converge to that point and then spread out is the same as the incident wavelength. So if it was light, the color of the light wouldn't change. So this is nice. So I'm just going to show brief segments of some of the other ones.
Showing up on the first page of Google.
What happens when you don't? What happens when you don't
For business owners, it is.
pay?
Take my Vintages online store.
It's reflection of circular waves. This one, where's the image of a point source that you put in front? Well, apparently, virtually, it's the same distance behind as the source is in front of the mirror, but they do a nice little 1964's animation here. I think it's on the next one they do. Yeah. And they time it also so that the time it takes from the virtual source. And again, also you can, whoops. Oh, there's narration.
Gorilla physics.
And you can show, by the way, that the angle of incidence and the angle of reflection are very close to one another. This one's sort of just visually cool because if you start in the center, the image is that's the pens that you fill the tank to the right. This is a little side point too. Actually, I'll go to the end here. The next one is one of my favorites, and there's special rooms that I've seen around. Okay, the elliptical reflector. And they start in the center of the ellipse, and you get this sort of cool reflection. But the person, she is looking for one of the focal points. And of course, if you're at one of the focal points and you had a light source, the light rays will reflect and head toward the other focal point. And this gets pretty close to showing that right. And there's whispering rooms where you stand at the focal point of a room that's shaped like this, and you get convergence of sound waves, in that case, to the other focal point. Okay. And I'm just going to move forward. And this one is, yep, here we go, commercial. Turn the sound off. Yeah, this free stuff. All these it makes the commercials interesting.
Students do find out a lot about their teachers.
Mm-hmm. Do they? Okay, now this shows waves. There's an overhead view, like all the views are, and we're looking, let's say, down on the waves. We could also be looking up on the waves, but I'll say down on the waves, and you can see as the waves go from one material to the other, they slow down, and the material here is a different depth of water. And the thing is, you can see the bending of the wave front, the change of direction as a wave goes from one material onto another, which they don't do this, I don't think, much anymore, but
back in the day, the PSSC books, for example, they used to start with light as the first topic, and you watched light, and you did different observations: light reflecting, light refracting, and of course we went from air to, let's say, glass or water. The direction of the light wave or light ray got closer to the normal, and if you say the direction here of the wave is perpendicular to the wavefront, you see that the line comes in like this, then bends what would be closer to the normal, or the wavefronts get more parallel to the boundary. And that would say, from a model standpoint, well, if waves are behaving the way light does, it refracts, then according to this wave model, light must slow down when going from air to glass, or air to water, into a higher index material, because that's the way a light ray would bend. One of the neat things was they went to the particle model, and you can show, there used to have a special ramp, where you rolled a ball at an upper level, and then it would go down a little hill and change its direction, and it would, if you went from the upper hill down to the lower hill, you got a new direction, and it got closer to the normal. But the ball, in that model, the ball was speeding up when it got closer to the normal. So you had a, excuse me, my mouth gets dry. You had a dilemma. Which was light? Was it wave-like or is it particle-like? And right at that particular point in the course, the answer was, we don't know. We don't have the ability yet to measure the speed of light in air or in water, or in some other medium. But it brought an interesting dilemma about models giving correct explanations, but under particular conditions. By the way, let me...
Well, is it okay if we finish off here? Because next we're over time.
Oh, okay. All right. This, by the way, let me shows that if you go from slower to fast, the direction bends, and you can just see here, it's going almost parallel. The direction is parallel to the boundary at this particular incident angle. And if you increase the angles more, you get, which is not easy to show in a ripple tank itself. They must have spent some time setting up here. You get pretty close to what would be equivalent to total internal reflection. And then one of the things is at the end, if you let it go, on the back of the box, it gave the explanation, including, if you wanted to try it yourself, an approximate way of setting up the ripple tank with the different depths. And you can see that the shallow...
A lot of the PSSC videos, they're usually about half an hour-ish long, and they cover a lot of great topics and done really well. So you don't have to use the film loops. These are a little longer, and they go into a little more detail, and they have some really nicely done videos that you have there. So what I have here is two neodymium magnets on index cards, so they're a lot easier to work with. And this is a $8 milligram or centigram scale. It's a jeweler scale, Amazon. So basically you can put one of the magnets on it, turn it on, and it'll read it as 0. So if I put this and this is an old lens holder. It doesn't work that well, but you can kind of get an idea. And then you go 3 centimeters above it, I can read the force at 0.1 grams, and if I go higher, I can read less and less force. And as long as you tape them in the same spot, you can line up the magnets there. So you can get force versus distance, converting centigrams to newtons. And then all I did was get here. So right now I have a Vernier magnetic field sensor, and I can go to the same height and measure the field. So you can plot force versus position and get your basically an inverse square law. And then you can plot force versus field and get a measure of the magnet itself. So I use this when I introduce charges because they've seen magnets before. They can't relate to charges. Yeah, Bill?
Are they little disc magnets?
Yeah, flat neodymium magnets.
The sheet, or it's a disc?
It's a neodymium magnet taped to an index card.
Got it. Because I was wondering if you had an area, you know, does it act like a point source? But yeah, it's the little thing.
It's the smallest neodymiums I could find. So basically they act as close to a point source as I can do. I know that magnetism, if you're close enough, works as an inverse cubic, but as long as you're more than about 3 centimeters away, you'll actually see the inverse square law really nicely. So you can get a inverse square law just with that to show them how this works, and they can actually do that, you know, 2 neodymium magnets, yeah, taped to an index card. And then this is an $8 scale on Amazon. Yeah.
I would hope you would have a discussion leading into this about the Earth's magnetic field. Do you have to calibrate that? I've never used one of those programs.
You just zero it. You zero it before, and then it ignores the Earth. Yeah.
Can you
Yeah.
get Earth's magnetic field just
So as long as I'm going to aim it this way, I zero it this way, and then the Earth's field's ignored, and it just looks at what's there.
But it will measure the Earth's magnetic field.
Yeah. So basically, that was the idea. So I used this when I introduced charges to kind of demonstrate everything. These were from a company called Weigram, obviously some cheap Chinese thing, but it works, so why not? So that's kind of the idea. So basically, those are the things you can do. The scale's on Amazon. The neodymiums, obviously, you know, you get them when you order your supplies. And the expensive thing is obviously the Vernier sensor. But if you have it, you can give them an analogy of field and force and how they relate to each other, which makes it a lot easier for them to understand electrostatics as we go forward. So that was it.
Kids, and it was a little bit more complicated than this one.
That was very cool.
Sure,
Then I
thanks.
finally saw how to build one of these, and I built this one. It's one of those devices where there's a hidden inside. And my friend who built one had it glued shut, so you could never open it and see what was inside. To really give the idea that in physics and in chemistry, we don't ever get to really see what's happening. It's all done by measurement and interpretation of those measurements. So this is one of those things, I'd be glad to have people play with it, fool around, just pass it around. If you want to know how it's built, you have to talk to me another day.
Don't bring that to the airport.
I know, it's worried about bringing you in here.
Yeah.
Demos. You're up next. We're back on time.
Thanks to Craig. Wait a minute.
That's cool. That's really cool.
Thank you.
That's really cool.
I'm Anthony Lapinski. I'm the outsider from New Jersey. Been teaching almost 35 years. I have a lot of demos. I could take the entire day, but I'll try to keep it 20 minutes. I present at the New Jersey AAPT meetings all the time, and I love what I do. I do a lot of weird stuff. Does anyone teach wave sound music?
Oh, I'm in it right now.
I'm in it right now, and so just to start, this is a little freebie for everyone. I've searched the world. I'm a big CD junkie. I got 4,000 CDs. I love 80s hard rock and all that. That's a whole separate discussion. So I've searched. I bought plenty of CDs from around the world, And so here's your own really waves and sound mini course here. I got your channel identifiers if you reverse the speaker wires to figure out which is which. I got in-phase and out-of-phase speakers. You can hook up 2 speakers and put microphones and hook up an oscilloscope. I use real oscilloscopes. I'm really hands-on. I make sound very visual. I got beats here. I got the Doppler effect from the Supersonic CD, which has recorded SR71s and things like that. My kids think I'm weird, but I'm pretty normal. So Doppler effect. Then I got all your waves here that you can check out beats with tuning forks. Get your tuning fork and hit it with this one. Things like that. I got the Trio Da 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 song that uses the Casio VL1. Claire Rockmore is the theremin. I have a theremin. It's the only instrument you play without touching, so kids get to play with that. And then A Very Silent Night was a CD from New Zealand. It reached the top 10 on the charts back in 2007. It's recorded above 20,000 hertz. So if you have some software, you can maybe step that down. I'm curious, what are on those 2 tracks? I've never heard them. And then what happens if you play music backwards? You know, play a piano concerto, tape record it, and then play the tape of the record backwards, and you'll see how the inflection goes away. So they've done it for you, and so that's kind of interesting. Then to tune your guitar, you have all the 6 strings of the guitar, and then some musical illusions and paradoxes at the end. Really interesting. From a woman out at UC San Diego. So here's an hour and 20 minutes. So check it out, and I use this all the time. I'm using it right now. It's a little freebie for all of you.
Is it DVD or CD?
CD. I know they have thumb drives. But I always have a handout because I always know when I go to workshops, where did you get that or what's the website? So I'm teaching sound right now. I played the trombone for 13 years when I was a kid. I never thought I'd be using it to teach physics, 40 years later. But I'm all low tech. I don't do any high tech. I'm low tech. I believe in hands-on. Today's kids are all TikTok. I'm hands-on. So here's the cheerleader horn. We talk about the main ideas of a wavelength, period, frequency. So I talk about how does a cheerleader horn amplify the sound. And they're not used to things like that. This is a diffraction phenomenon. I'm basically making my mouth wider. The formula for this is sine theta is lambda over d. So if you make your mouth really wide, it makes the diffraction angle much smaller, like so. Again, we're getting to something mechanical here now, electrical. So then I bring out this, and of course they're all thinking, you know what they're thinking. Like you see this in college, obviously with fluid dynamics. So I don't allow cameras in my classroom at all. We have a big problem with cameras and phones because kids always want to be on the phone. We're here to learn physics, and physics rules. Okay, so here we go, same deal here. I'm leading up to an instrument now. You probably hear me really clearly, but if you're from a right angle, you don't really hear me. Kind of like so. Like I certainly play a trombone like this, etc. So again, this is stuff I just get out of the garbage. I'm a big dumpster diver.
Can you stick it in your mouth?
What a great.
You just gave me an idea for a cartoon showing a guy with a big mouth and a small mouth, and which one is yelling?
That's right. And then Target sold this for $16. Someone told me in the New Jersey group. So it's a mechanical amplifier. There's no wires in here. So you just take your iPod. You know these iPods? And I always play songs that I like. I don't care what they like. I play my music from the 80s, of course. So here's the little speaker, which is pretty loud. It spreads it out in a million different directions. But if you put it in here, again, there's a little hole there for the speaker to go in. So again, this is all diffraction leading up to the instruments. And that sounds pretty good, Everyone knows it. But not that bad. I saw them live. I love the 80s. So this is into the Vuvuzela. This is now banned at many sporting events because 1 meter away, the sound level intensity is 120 decibels. If you look online, it'll give the whole list of events where you cannot bring this. So 120 decibels at 1 meter away. So, so here we go. To create the standing wave, I have to sort of, I'm buzzing into it. So if you keep doing this, saliva is going to come out the other end. Kids hate that, but I got their interest. You hear it really well. Those over here can't. So again, when you use the megaphone, you sort of have to. There's a drawback. You're getting all the sound here, but you're not getting over here. Whereas when I talk now, everyone can hear me. So.
Can you point it towards the door and show us?
Sure. Okay. I'll try. You might be able to hear it. So. You can get these cheaply online. So the bulk of the handout deals with the trombone here. The trombone's instrument. Does anyone play a musical instrument? Oh, excellent, right? If not after today, you'll want to get one. So all musical instruments behave like they are physically closed. I'm putting my lip through, which essentially closes the pipe. Here's the open end. The catch is that the conical shape of this leading to the end changes the standing wave pattern and makes these instruments behave open. How do I know that? When you look at all the notes that I can play or that can be played on the trombone, it doesn't follow the closed pipe rule. There's the first three positions, and the first note's very hard to play. I did play it back in the day, but you can clearly see the harmonics there. They're all integer multiples of the fundamental, not odd multiples. So this behaves like an open pipe, yet physically it's closed. All instruments behave open except the clarinet. The clarinet is the only one that's nearly perfect tube. It truly behaves like a closed pipe. I did the formula here. You can actually measure the length of the trombone. Who would do such a thing? 2.75 meters. So the fundamental should be 62. Should be, but it's actually not. It's 58, and that 4 hertz makes all the difference. So now put in the real frequency, 58. And you get the effective length of the trombone is really a 2.95 meters. So it actually extends it an extra 20 centimeters. This kind of goes a little beyond my high school physics class, but because I really don't go into this. We just do basic open pipes, basic closed pipes, So we also talk about tuning valves, things like that, to make them to make it a little longer or shorter. I played in marching band, and we had to blow into the instrument to keep the instrument warm on the 50-yard line back in the Chicagoland area where I'm from, so that the instrument was warm, so by the time you started playing, it stayed warm, and the audience didn't care, but we knew if we were out of tune. So I talk about the speed of sound and air, things like that. So that's your basic trombone, brass trombone. These run for $300-400. So now the plastic instruments. These are plastic instruments here. The P-Buzz is called a P-Buzz. They get for $30, but if you write the company, you can get it for free. I love writing companies getting free stuff. I'm trying to get a free electric car. I'm trying to get that. I've gotten a free Dyson fan. Those retail for $275. I love getting free stuff for kids. So this is the P-Buzz. I got information on here. This is meant for kids. As they're learning the instrument in middle school, but again, it can be for adults, things like that. It actually tells you what note you're playing. You can measure the length of the tube. Again, the conical end here, it's going to make it behave open, even though it's physically closed. So, and the kids are just learning how to buzz their lips. I'm physically spitting in here. I can't blow. I have to spit. So conical. And I use mutes. I use mutes in my trombone to make it louder, softer. Talk about that. So again, I got this for free. I actually got 2 of them for free. And this led to the plastic trombone called a P-bone. Plastic trombone. These retail for $200. You can get them on Amazon for $150. But if you say you're a teacher at musicarts.com, I got it for $100. They come in 8 different colors, but the slide is always black. So I wanted it all to be black, but you can get your school color, you can also paint but the slide's always gonna be black. So, but it can be painted. At the end of these last, few centimeters, the slide's really riding on that to grease the friction. So this is just a smidge thicker, a little wider, so that it's all riding on that. So, and this behaves just like a regular trombone. Of course, the kids all want to know how it sounds, as you all do now. So, do you think it's going to sound any different from a regular trombone?
I hope so.
Okay, $100. Here's the original. And now this one. You can also start this in reverse. Tell the kids to close their eyes and then figure out which one you're playing. But, you're all pretty sophisticated. I was always surprised at that.
Yeah, me too.
It sounds like a brass instrument. That made it even better. It's also lighter. It's not going to break things like that. It's just better in the long run. And the company's green. They're a carbon neutral company, so which is kind of neat. Again, it comes with a matching mouthpiece and a clear mouthpiece. Again, they got 8 different colors for your school colors, but the slide is always black. So I didn't want to clash because we're blue and white at our school. So I am going to bring this back to school on Monday and be teaching about strings and open and closed pipes. So, how about questions? Anyone have questions? Yeah.
And where did that little toy trombone come from? The one that's
P-Buzz? That's the P-Buzz. I think the website's on there, yes?
Yes, it is.
So the websites are all on here. I wrote P-Buzz and they gave me 2 for free. I wrote, again, it's made by Warwick Music. This is a UK company. They're not made in the US. That's why it's there. If you want to see the history of how I got to this, then they sent me the US website, which led me to Music Arts, and then I contacted the guy at Music Arts. And then those 2 last websites, they have educational discounts. Just tell me to teach physics and all that jazz. And I couldn't get one for free, but again, I got it for $100, which beats the Amazon price.
But it's only 2 inches long.
So,
Is there any instrument, maybe a question for everybody or anybody, is there any instrument that will basically model a closed resonance tube?
the only one is a clarinet. That's the only truly closed instrument that behaves closed. All other instruments behave open, even though they're physically closed. So again, I didn't find this out till my later years in life, but you can clearly see the trombone physically closed, but behaves open. So again, I briefly mentioned this in my classes, but I don't get involved with it because kids don't care. They just want to know. They just want to do math problems with closed and open parts. But I have a physical example for them. It's pretty complicated. I forget the website. I should have listed it. There's a good website that shows why and how these standing waves go from closed to open because of the way the sound reflects from this end that gets wider. And as a teacher, I like to learn new things, and then I like to share my passion with everyone else. And again, physics rules.
Yes.
Don't let any bio or chem teacher tell you otherwise. Physics rules, yeah.
With the funnel, there's also a sort of reverse thing that you can do, which is if you put a narrow line, jam it into the ear, but just put it next to the ear, and then it's good maybe put somebody on a rotating turntable or rotating seats like these, and have a source of sound, and compared to just your plain ear, you're not terribly directional because you have that small opening in your ear, but when you have the big opening there, it also acts as a very directional receiver.
When you're up in the trees, and they have these big earphones that you put in your
It's basically the same idea. It's
Yeah.
amazing how much you can hear.
Yeah.
You can actually hear the trees moving, or you never.
You can point a person and tell them, stop rotating
Yeah.
when the sound's the loudest, and they're almost always dead on to the line between the source and the megaphone.
Somebody makes a noise across the room. And see
I can hear you breathing. That's all you need to say and you got their attention. I really can. You put this up against a wall, you can hear things in the ground, which leads to the stethoscope demonstration, things like that.
Or the old water glass against the wall and detective stories.
So again, enjoy the CD. I do have extras if you want.
Thank you so much.
Thank you.
I'll take an extra because I'm
Sure.
a resident teacher. Thank you.
I believe in free.
Ronald.
Which turns on the front lights?
This one, you want the front lights on, yeah.
So, hi, I'm Ron Pedelty. I teach at Westchester East High School. There's a really wonderful series of physics, or not just physics, but science lectures called the Science Bag at the University of Wisconsin, Milwaukee. Their science faculty host these evening lectures on topics of their interest for the general public. And one of the really good ones is called the Wash Tub, the something, and the Nailolian, the physics of musical instruments. And it really is a great, takes you from because it's for the public, and you can see there are children and stuff in the audience, takes you from no knowledge of waves or sound at all, and works in about 1 hour with hilarious demo, like there must be 50 demos to the physics of string instruments, percussion instruments, and woodwind instruments. So if you're into it, it's called the Wash Tub, the something, and the Nailolian, the science of musical instruments, something like that. It's called Science Bag, and they've got really good videos on a whole bunch of why does the spinning top stop. It takes you from no knowledge of rotational motion all the way up through moment of inertia and torques and stuff, and it's all really, really entertaining stuff. So
University of Pennsylvania, you said?
No, it's University of Wisconsin, Milwaukee.
Yeah.
Yeah. So anyway, my demo is going to be about momentum. This is a demo that I have to get permission from my faculty and stuff to do, so I checked to make sure it was going to be all right to do it here. But I've got two soda cans that have soda straws on them. I grew up, or I taught in the Chicago area for a long time. It took me a while to learn to say soda instead of pop.
Wow. Gym shoes, sneakers.
Yeah, exactly. And water ice, that's what's on the street in the wintertime. When you say comets are made of dry ice and water ice, and everybody goes like, water ice in comets? Well, okay, so it's water ice. Yes. So what I'm going to do is put a firecracker between the two soda cans and set the firecracker off, and then we can do conservation of momentum, that way. And I will usually get 4 students to help me. I've got a plumb line here that I'll drop, and then some students said, "What are you doing this weekend?" I said, "I'm going to do the firecracker demo for some physics teachers." They said, "That is the coolest thing we did all year." In a few weeks after the AP test, we're going to make holograms. I don't know if you've ever done that, but you can do it with a solid state laser and some holographic film. It's made in Russia, so the supply chain is a little bit slow there, but it's the other coolest thing we've ever done in physics, and it's not that hard to do. To make holograms in the dark on actual holographic plates with chemical baths. So, but this is a close second, I think, for popularity. So I'll put the firecracker between the two soda cans, and then if the total linear momentum to begin with is 0, and if the force is more or less through the centers of gravity, centers of mass, I should say, right? Linear. Yeah, exactly. I saw Bill Berner blow up a house.
Yeah.
So, so this is probably small potatoes. You can do that.
And I never asked permission.
And you never had permission. But you were more indispensable than I am in my school. So anyway, the total momentum to begin with is 0. So after the explosion, the total momentum should still be 0. So M1 V1 final should equal M1 V2 final in magnitudes. right?
Are the cans the same mass now?
And they are, well, it doesn't even matter, right? Doesn't even matter. MV and MV are gonna be equal in magnitude. And they're probably pretty close, but I'll have 4 volunteers, we'll lay 4 or 5 meter sticks out that way and 4 or 5 meter sticks this way. Just make sure you don't have any of them backwards. I mean, there are those little things in a classroom. And I've got a plumb line, and then I'll have 2 students wearing protective eye gear to see where the can hits, and remind them it's not where it stops rolling, but where it initially hits. And well, I'm not actually going to collect data. Everybody's looking at their watch. We're not going to really collect.
You're afraid to miss if it works.
What's that?
You're afraid to see if it works.
And there's, here's how you properly do the chimney cart lab. You say, if the ball pops up while it's rolling, shouldn't it land in the chimney? They say, yeah, it should. You go like, fine, and then you put it away. That's the correct way to do that. You're always afraid to actually try it. So.
It never works like it usually
It never works. In fact, it was that general that the teacher said that with some frustration. It never works the way it usually does. I always thought that was really interesting. That's an interesting comment. Why did it never work the way they usually do? All right. So then the next thing I go through, and of course you guys, we all get this, but it's a good thing to go through with the students. M's are pretty easy to find. So I've got 2 students with the goggles watching to see where it lands. I have a student and a scale. And every time I add mass or take mass off, I just put some little brass masses on there. They find the mass, and then I have a 4th student who's using the whiteboard to record masses and distances. And what was I going with that? I don't know, so something interesting about that. So here's the thing. Masses are easy to find, but velocities are pretty hard to come by. How are we going to get the velocities? Well, we could say this. If they have different masses, and in some of our trials they will have, how's that going to affect the amount of time they're in the air? And we can talk through that because they should know by now that, in the absence of appreciable air resistance, a paperclip in a textbook will not fall at the same speed. I hate saying that because it's a lot of different speeds as it falls. They'll fall at the same rate or with the same acceleration or take the same amount of time to fall the same distance. So that's not going to have an effect. And then I can also say, what's that?
That's a great way to double check.
It's a good way to double check it. And then the other thing is, one of them is likely to be going faster than the other. How is that going to affect the time in flight? Well, if I'm careful to have this horizontal, then they should fly, over horizontal level ground. They should be in the air for the same amount of time, regardless of the speeds. So I say what we should hear is bang, clunk, not bang, clunk, clunk. In spite of the fact that you have different masses and different horizontal starting velocities. So that's a pretty cool part of this lab. And then, so I'll just set this off because why else would you have firecrackers and stuff in class? And we won't collect any data. But you can see it's kind of a crowd pleaser here. And then I always have to shout fire in the hole, make it very dramatic. So fire in the hole. There. And we do that like 6 or 8 times. So then the other interesting thing in a physics class is you predict what you think should happen, and then you can always do an experiment to see if you were close. And then the question is, what does it mean to be close? Were we close? Is that about what we wanted? So then, what does it mean to be close? And I'll sometimes use an example about, I said I made a measurement over the weekend, and I was really disappointed because I was off by 4.5 miles. And they're all like, I said, is that good or bad? And they're like, well, that's not very good. What were you measuring? And I said, the width of the continental United States, from the Atlantic. Oh, well, that's not so bad. I said, oh, I feel better, good. Because there was another measurement I made I felt really, really good about. I was only off by 1.5 inches. And they said, what were you measuring? I said, the width of human hair. And they're like, oh, that's terrible. So you always want to compare your error to the size of the thing you're measuring. Your error is if you subtract, and comparing it is by dividing. I don't want you ever to ask me, should we find % error? Yes, of course, you should, because how far off you were tells us nothing. And what's that equation again? You should know. You're going to subtract to find out how far off you were, and you're going to compare it to the thing you're measuring. Right? So on this one, an interesting question is, we'll get our results. Is it close? What does it mean to be close? So what I've decided is, We just reasoned through that if this one has 1.7 times as much mass, that has to have 1.7 times the velocity. So it should go 1.7 times as far. So m1 over m2 should equal d2 over d1. And if we divide m1 over m2 by d2 over d1, it should be close to 1. And we'll do this like 8 times and find all those ratios, and they'll be like a smidgen under 1 or a smidgen over 1 and average them all up. And we'll find the average of that ratio. It actually comes out surprisingly good, like 1.03. So it's you wouldn't think you'd get such good results. The last thing is, oh, by the way, if you're going to do this, it's pretty easy to put together. But I send out an email a couple of days before and the day of, because if there's bang, bang, bang and children screaming, we're going to make the 6 o'clock news. Not the way I want. So that's a serious concern. Make sure everybody, as it turns out, those classes across the hall never heard anything at all. Wow. But, and by now they're all used to it because I've been doing this for like 20 years. So they go, oh, it's just going to be Pedelty.
So a can of Coke and a can of Diet Coke, because the Coke
I suspect both of them are just going to,
M80.
I suspect both of them are just going to sit here because that's a lot of mass and a lot of friction. These are empty. These are empty. No, and then the last thing that's after you do the whole demo, you've got a really great demo of inertia because the back ends get all bent up, which means the back end started moving before the front end started moving. And there's the physics principle of locality, that the only thing you know is what's impressed on you, right? You can't see light before it gets to you. Is that what that's called? I think it is. So the front end doesn't even know that the firecracker has gone off until that wave, that shock wave, has gone to the front. And you can see videos of giant slinkies that they let go, and the bottom doesn't fall until the information gets to it. And the crazy thing is, it's just if you drop a pencil, the bottom hangs for a moment in the air until that information reaches the bottom that the top was released. Nothing travels faster than the speed of light.
Would it have to get to the front or the center of mass?
No, it has to get to the very end. Like the whole time the center mass is falling at G. But for a while the top is falling faster and the bottom's not falling at all. All right? Yeah. So just watch. You can watch these videos of slinkies falling and the bottom doesn't move, but then take a ring stand pole and drop it and the same exact thing happens. The bottom hangs for a little while until, so anyway, I don't want to use up any more time, but just passing the cans around, showing that big dent is kind of a cool demo of inertia and stuff like that. All right, that's it.
Just hit HDMI button.
I think I did.
Skip a second. Just like,
There it is. All
it
right.
takes some time to adjust.
All right, so I'm the last presentation, so I think that means that I give the final exam. Yeah, so this originally started out as like an hour-long talk, so I started paring it down. And then I remembered I basically gave this talk last year, so I decided to go in a little bit of a different direction with it. So Fermi questions for the uninitiated. These are essentially order of magnitude estimates. If you can't come up with an accurate answer, sometimes we call them back-of-the-envelope calculations. Maybe it's an estimate of feasibility. Is something even feasible? Is it within orders of magnitude that you can do it? You may be estimating something when there's very limited information available. You're also taking very complicated problems and you're breaking them up into more manageable parts. So sometimes what we call the spherical cow approximation. But remember, you have to assume that when you make the spherical cow, you're not missing any important details. So some ideas that come out of this, and I think this is useful for students to kind of understand, thinking like a physicist, dare to be imprecise, right? Come up with upper and lower bounds. What's the lowest value I think it might be? What's the highest value it might be? The notion of the geometric mean, right? We're used to the arithmetic mean. The geometric mean of 1 and 100 is 10.
So a couple of the principles here. So confidence intervals and getting really good at converting units, getting a feel for large and small numbers. And then where I decided to go with this was to talk about scaling in physics. So I think this is a useful exercise for students. So how does one quantity scale in relation to another? So probably linear scaling is the thing that we're most used to. And usually we're pretty good at dealing with that. Right? So if I could walk 3 miles in 1 hour, how far can I walk in a day? How many songs does a radio station play in a year? If I built a stairway to the moon, how many steps are there? Right? Things like that. We're usually pretty good at dealing with that. But then if you have things that scale quadratically or cubically or exponentially, we suck. Right? This is why the jelly beans in the jar is always a winner at the carnival, because no one can guess that number. And of course, exponential is the worst of all of them, right? That was like COVID, 3 years ago. Oh, there's only 48 cases. That's no big deal. Yeah, but there's 20, a few days ago. Yeah. So scaling in physics. So a nice little example of this is flight. So the lift of a wing goes as the dimension, which is or rather is the area, which is the dimension squared. But the weight that you have to lift is proportional to the volume, which goes as the dimension cubed. So as the bird gets bigger, the lift to weight ratio gets smaller and smaller. That's why you got a little hummingbird here with its little tiny wings and just flaps like that, and it can fly with no problem. Here's a bigger bird. It's got to have really, really big wings in order to maintain flight. And then you get a little bigger still, and they can't fly at all. That's why no matter how hard I tried, I wouldn't be able to fly. Even if I put big wing flaps on my arms, I would not be able to fly.
It flies when it jumps.
The emu, they can...
No, when it jumps, it flies in free fall.
Yeah, they might be able to do a little bit. You have like some of the mammals. Yeah.
I actually did the impulse momentum calculation. A human can fly if you flap your arms at 43 times a second. It's a impulse momentum, except the forcing your hands would be about 30,000 pounds. You'd rip off your tendons. But I have the calculation. Hang on, 43 hertz. And no one can do that.
Yeah, so another example of this, sort of the same idea. If you look at an animal like a mouse, it's got these little thin legs that it's able to jump and run really quickly. But then you scale the mouse up to a larger size, it would just collapse under its own weight because the strength of the limbs is proportional to the cross-sectional area, but the weight goes as the volume. So that's why an elephant has the big tree trunk legs and has to be in the most maximally stable position like that. So now you could imagine some other things like, what if we were on another planet with a higher or lower value of G? What would animals look like? Maybe a planet with very high G, you'd have mice that look like the elephant, or maybe something that's more or less flat, right? Because that's the easiest way to get around that.
As an aside, if I don't mind interrupting, the larger something is, the longer it takes to cool down, because it's the surface area volume ratio. This is why elephants have big ears, and that's why small mammals eat like crazy. And the Earth's still cooling down, but the moon's cold. So.
Yeah. Yeah. So why are there no large insects? Right? They breathe through their skin, which is the surface area. So the larger the insect gets, the larger the ratio of mass to surface area becomes. Notice that I say, why are there currently no large insects? So what would have to change if we wanted a planet with large insects? What would have to be different?
O2 level.
The O2 level. So there were periods in the past, I think it was the Carboniferous period, where there were large insects, because the O2 content of the atmosphere was like 30%. Something like that. You also had no large mammals or birds to compete for those big...
You need to quote the appropriate reference. The guy who publishes most of that stuff is named Berner.
Berner?
And he's unrelated.
It makes sense, because that's what happened to forests, 30% oxygen level.
Yeah. You could also increase atmospheric pressure. Actually, we do have large insects right now. They live in the sea. Right? Lobsters are the cockroach of the sea. Yes, another interesting thing. Why can an insect safely land after it drops from a great height, but a larger organism cannot? The air resistance, right? That goes as the cross-sectional area, whereas the weight goes as the dimension cubed. Right? Same idea, hammer and a feather, right?
Yeah.
The feather has a large ratio of surface area, or actually cross-sectional area, to mass, whereas the hammer has a much lower ratio. We live in a 3D universe. Light and gravity, all that stuff obeys the inverse square law. How are those related? Why does one follow directly from the other? Yeah, so if you imagine a light bulb, if you imagine pulsing a light bulb, there's a sphere of light coming out. Surface area of the sphere goes as r squared. So as the light goes out, it's the same number of photons distributed over 4 pi r squared, hence 1 over r squared. What if we lived in a 2D universe? It would be a 1 over r. In fact, you do get that if you have a linear source. You get a 1 over r. If you're in a 4D, 5D universe, you can do all of that. Some other scaling things. This is kind of an interesting one. This sort of gets back to how we don't deal with nonlinear scaling. How many tiles, 12 inches across, would it take to tile this room? You'd have to think about it, and if you just tried to guess a number, it would be way too low. You'd come back from Home Depot and you probably would have about enough to do this section. Because if you guess like 100 tiles, that would be a 10 by 10 area, which is pretty small. Even 1,000 tiles.
Let's say this is like 20 by 40.
Yeah.
Yeah. Yeah, it's probably 1,000, give or take a little bit. How many golf balls could you fit in this room? Bill, is this an exercise you've tried? How many things you could fit in a room?
Golf balls are
Yeah, yeah, you'd probably get a couple inches off the floor and realize you're about done. I think of what else. Yeah, as far as the insects go, another and you were kind of mentioning this. Reptiles, for example, need a lot of help with thermal regulation. So one of the ways that they do it is they have things like frills and sails that come up so they can change their surface area. Right, so you're changing the ratio of surface area to volume, so it's like fractal dimensionality.
Our students were kind of trying to work on some scaling stuff yesterday because they heard about I don't know if you guys heard about the dimes that got stolen. Somebody stole 2 million dimes from a trailer in North Philly that was parked in a Walmart parking lot that was going from the Philadelphia Mint to somewhere. So the kids were trying to figure out how much space and weight, but then they got onto like how much space would 2 million dimes take up.
It's actually not much. It's like 100 by 100 by 100, right?
But it's also 5 tons of dimes. The
Yeah,
dime
the
reads
weight
like a
is
physics
also
problem.
a problem.
We spent most of the afternoon texting back and forth and asking physics classes about these dimes.
Did they get close?
Yeah, but well, as the article updates, they had 1 pickup truck, 10 people, and 5 tons of dimes, which brings up the question, like, how do they get away? Like, how are you even getting 10 people into one?
But we were in the
Another
wrong
white
state.
car.
I mean, if you went south, there was a
That's
guy
so
throwing
I know,
$100
the same
bills out the
thing.
window of his car.
Oh, man.
By the way, dogs a good example in India.
Panting, yeah.
Because they do not
They don't sweat, yeah.
Because he was pissed at the fan.
Yeah, Mark.
As far as golf balls, it would depend how you pack them, so you get the crystalline structures.
Well, at that point, you're talking a factor of 2.
Yeah,
Right,
it's
between-
just a coefficient.
Or not even that, between simple cubic and close packed. Yeah. Yeah, usually people are up by like a factor of 10 or more.
I also teach astronomy, actually in a planetarium, and you can get 110 Earths across the sun. So if you cube that, you can get 1.3 million
Million.
Earths inside the sun. It's pretty far out.
A couple of examples here to think about. What modifications would have to be made to the human body if human beings were 50 feet tall? How would we be different?
Stuff on both of
Oh, that's tough.
Bulbs.
That'd be working
Yeah.
hard.
Big, heavy legs, probably.
And a lot of flesh,
Yeah.
like sailing.
Yeah. Surface area would be an issue for sweating, things like that, so thermal regulation. Blood pressure would be an issue too. The pressure difference. In fact, I was reading about this. Giraffes apparently have blood pressure. It's like 300 over 180 or something like that. Some crazy number that the blood pressure at the heart has to be that high to maintain it at the brain. So you have to have much thicker arterial walls.
I think at this height they will adjust to capillarity, delivering the...
Yeah, there has to be adjustment too because the giraffe's head can go up and down.
Yeah,
Right,
but
so you
I
get
mean,
300 over 180 when you're up here, 300 over 180 down there.
People with this height will always be straight.
Yeah.
They cannot bend.
Yeah, you would. Yeah, if you bent over, you'd have enormous pressure at the
And then you're
brain.
talking about transmission of impulses through the nervous system, that would be affected because it's going to have to be.
How slow it would be. So if you step on a brontosaurus's foot, you got some time to run away. Yeah. Little astronomy example here. You have two stars you're looking at in a telescope. They're orbiting one another, so they're the same distance. One of them is red, one of them is kind of whitish. They appear to be the same brightness. Which star is larger and by how much? Interesting scaling question. The input that you have to put in there is that the luminosity of an object goes by the Stefan Boltzmann law, so it's proportional to the area and to T to the fourth, the temperature to the fourth power. So you look at the ratio of the temperatures, and then you can figure out the ratio of the areas, and then from the ratio of the areas, you get the ratio of the diameters. Kind of a fun trivia one here. Enterprise approaches a new planet. It enters an orbit just above the cloud tops. Most of the sensors are broken, so they know nothing about the planet. Yeah. They complete an orbit in 90 minutes, and right away Spock says, Captain Kirk, this planet is made out of rock. How did he figure that out?
It's about the Earth, 90 minutes.
Yeah, it's about the same as the Earth. It turns out that the orbital period depends only on the density of the planet. Everything else scales out.
It's the same like you drill a tunnel through the Earth. It
And
will
do the
take
period.
exactly the same time.
Yeah, so a couple of interesting ones. These we're getting more into the Fermi questions. The largest asteroid you could jump off of and escape its gravity.
Why? It depends on jumper.
Because G depends on the radius and it depends on the density. So actually smaller asteroids can actually have escape velocities of like meters per second. Or you could even run and you'd actually go into an orbit around it.
That's cool.
A couple of scaling type things. How big a solar panel would you need to supply all the US's energy needs? Laid out all the atoms in your body in a straight line. Turns out it's pretty long. Yeah. If you were dropped into a random place in the continental US, on average, how far to the nearest state border? It's a fun one to think about. Just airdrop somebody. Yeah. How long could you survive off the food in a grocery store if you were locked inside? And that brings up questions. Is the power on? Yeah. Yeah. Something similar to the pennies. What volume of snow lands in Pennsylvania over a year? If you made it into a giant snowball. Well, yeah, this year 0. Kind of a fun one I remember from a chemistry book back in high school. When you breathe in, how many of those atoms were breathed in by Abraham Lincoln during the Gettysburg Address?
That's like Caesar's last breath.
Take all your money and pennies and melt them into a solid sphere. How big would the sphere be? How many U.S. presidents, past, current, and future, are alive right now? The future one is what makes it an estimate rather than just knowing the number. Yeah. How many dentists are there in the U.S.? Kind of an interesting one. Yeah, so that was basically it. So just some ideas about scaling, maybe bringing some examples up in classes. Yeah, Ron.
When you're doing this, one of the amazing things is like the things that are squared or cubed. Stefan Boltzmann's gives you an exponent of 4. If you're looking for higher exponents, they're hard to find. But I've been told, it's always risky when you say that the amount of silt that a river can carry is a 6th power of the velocity of the water. So when the Mississippi gets down to New Orleans and slows down and that silt drops out, if that's true, that would be one of the kind of unusual high power relationships that would be interesting.
Remember, there's a few in astrophysics. The rates of fusion as a function of temperature, they can be very high, like 20th power, things like that. That's why you get very unstable stars late in their evolution, because the burning rate goes as like T to the 20th, so your temperature changes by a small factor, and now you become 10 times brighter. Other questions?
Is there a handout for this?
No.
Or a site or anything?
No, I didn't put anything together. Maybe I should.
Maybe you could post that on the website?
Yeah. Actually, I have a bunch more of these that I got rid of.
If you want to send it to me, I can put it up as a blog post.
Yeah.
And just have blog post the Fermi questions.
Yeah.
Oh, that'd be great.
And then other people can put them in too. Yeah, most of these I don't have answers for, so it's sort of like a road trip, right? It's not so much the answer, it's how you get there.
No answer keys?
Yeah.
How do we teach?
Of course, you have the Drake equation. which is kind of the ultimate Fermi question. And usually when you do that, you get answers that are all over the place. And that's even though we now know so much more about the astronomy than we used to. You know, like the number of habitable planets, and like we actually have numbers for those. It's, you know, how long does a civilization last? And, yeah, especially the last couple of years. I don't know. I've had a lot of doubts about that. Yeah.
I'm afraid we're getting the answer.
Yeah. Fermi's paradox is real. Right. All right. Thank you.
Thank you.
Thank you.
Public service announcement. So there was an email about this in March, I think maybe February. I was a high school physics teacher for a long time, but akin to what you've been hearing Bill say for years, I woke up one day and I was in a Valhalla of decadence, and we have all of these things. So my day job now is promoting active learning in the undergrad physics classes. Which is, I don't want to heaven get to just try to convince professors to do better things. Active learning to me is a funny term. You learn whatever it is you are active doing. So take from that what you want. But the reason I'm here to talk to you is the other half of my job, which they call outreach, but I think of as the gentrification amelioration line item in the budget. I'm tasked with going out into the physics community in West Philly, helping the teachers, whatnot. The other thing you probably know, if you've been coming for a while, is we do a summer program for high schoolers, where about 36 high school kids who are about to take physics or just took physics come. It's an international cohort. They come to Penn's campus and for 3 weeks are full-time with us, and we basically do all of undergrad physics in that 3 weeks. The reason I'm talking to you is I've convinced the brass to set aside enough money to hire 2 high school physics teachers per year. This is the first summer we're going to do it. I had done this, right? But I sort of wormed my way in and never left. We are going to be very intentional now about grooming and helping and supporting new high school physics teachers as they come into the fold. You know, I could quote you all kinds of research. The support is like monumentally meaningful for the longevity of someone's career and the success of learning in their classroom there. So they're gonna, it's a fellowship. And I should say, we've named it after someone in the room. It's the Bill Berner Physics Teaching Fellowship. So, someday when we're all gone, someone, if this is successful, will be saying, "Oh, I'm a Berner fellow. What does that mean?" And they're going to Google, if that's still a thing. So here's what it is, and I encourage people to apply. The language we've settled on is, ideally, it's a new career physics teacher, first 3, 5, 6 years. We've had a good response. There's no hard and fast number on that as yet. So I'll describe what the teachers will be doing. First year you come in, you're sort of a semi-observer. You're not going to pitch in and do a ton of teaching. We're going to bring you into the labs and expect you to be talking with kids. And to do some instruction light, right? But you're going to be there full time, and you're going to come in a week ahead of time and get acclimated to how we teach this program. But the real value, I think, is after July ends, this is 3 weeks in July every summer. After July ends, what we're going to do is very intentionally come back with you to your school every 6, 8 weeks, whatever you want. And we're going to have picked some unit that you want to develop as part of your regular teaching duties in a school like this. And we have equipment you probably can't buy, right? We have expertise that you maybe haven't developed yet because you're new. So we're very intentionally saying we are your teacher education program in lieu of one. And we all also know that typically you are one of 1 or 2 or 0 physics teachers in your school. Maybe you're a math teacher doing this. And you need community, right? Like, so we're very intentionally trying to build a community of physics teachers, as we all are here. So you're gonna get support from us in that school year, and then you come back for a second summer, and by then someone will have come up behind you, and hence, there's always someone coming in and someone leaving every July. So there's gonna be 2 fellows in perpetuity, is the idea. So if you know anybody who should apply to this, originally I had said mid-late March is the deadline, but the real deadline is May 1st. We have to have picked someone and hired them before June. That's our absolute drop dead cutoff. It's going to pay $5,500 per summer. Yeah, I'll send the email again. I'll send the application again. Any questions?
Yes.
Yeah.
So I have a resident teacher.
What's that mean?
Resident means she's stayed with me for the entire year, so now, next year, she's got her own teaching position, so you don't need to have already?
No.
No, so she would be a good candidate.
Yeah, we would determine if we reasonably expect that you are going to be a physics teacher. That's our only criteria.
Okay.
Yeah. So what you're telling me is she's going to have her own class.
Yes.
And we know where that's going to be.
It's going to be at, oh my goodness, I'll get back to it.
But local.
Mansball. No, it's not Mansball. Go ahead. I'll think.
There was one.
I was just going to suggest that you might want to make it open to people who are teachers but are new to teaching physics, and people who are new to teaching.
Yeah.
That was my case. I was a chemical engineer, and I came into teaching physics, and the one who left nothing for me.
I hear you loud and clear.
So this group really saved my career 40 years ago. I guess they're.
I have a similar story. I was an engineer who started teaching in 2007. How old was I then? 30? Yeah. Career change. And my first AAPT meeting was April 2008. Gino Segre was the Friday night speaker, and it was phenomenal.
Jim Nelson was my first real contact.
All right.
For kids, what's the name of the program?
Oh, kids. EPRA, Experimental Physics Research Academy. It changed names from when I used to do it.
It's not LENS?
No, it used to be PSSA, but now it's EPRA, EPRA. Oh, that's the other thing. For students, if you have students, they should consider this. The tuition's a little steep, but we have a mandate to have 10% scholarship students. So, for perspective, when the application opens in February, they told us within a week they had to close our application because they had 80 qualified student applicants for 30 spots. By contrast, for local scholarship students, they'd left that open because they hadn't had enough. So, encourage, don't let them see the price tag and not apply. This is for next year, obviously. We're all set.
Experimental Physics Research Academy, EPRA.
I'll email all this, but I saw one more hand. Thanks, Will.
I can't quite read that.
Sorry. Experimental physics research.
Ryan, it's